So you were like fishing the water there. You were like fishing the water. You were speaking in Spanish.
Well, they speak Catalan. They speak Catalan.
Okay. So what I want to do in this session is not go through in detail an exam paper, but I want to show you an example of the exam that you're going to be set. In fact, I'm going to show you last year's exam. And I'm going to talk through what I'm expecting for the answers for a typical exam like this one. Some of you haven't done exams for a long time, and this might be new. And some of you haven't done exams in the British system. And some of you haven't done exams in the Newcastle version of the British system. So what I want to do is give you an indication of what I'm looking for, because it'll be me basically marking the exam together with Professor Gibson. And Dr. Euler is marking your assignment. So I have my own ideas about what you should be doing, and I'm going to tell you those today. So that's the idea behind this. So I'm not going to give you a detailed answer, but I will tell you certain things for this paper. Now, of course, it won't be the same paper, so I'm not going to sort of give you the answers to the exam this year. But I will say that if you look at past exam papers for this module, and there are some available on Blackboard, on the exam website, they'll give you a very good indication of the sort of questions that will be set this year. There's only a certain type of question that we tend to set, so it won't be too different from what you've seen before. So the first thing to note is the exam time is 2 hours. So be prepared to be working for 2 hours. The biggest criticism that I've had with people in the past is the people who have written something and then left after an hour, and they haven't written enough to get the marks. It's not what they wrote was wrong. Generally what people write is correct, but if you don't write enough, you don't get the marks. So that means that you need to make sure that you know at least enough to be able to collect the marks. Now, the way this paper is structured, it says attempt question 1 from section A and 2 other questions from section B. So question 1 is compulsory, that means you have to do it, and it consists of a lot of short questions that you have to describe. Now you can choose which of those you do, but you have to do some of them. And you want 5 parts of question 1, each worth 10 marks. And then you would have to do 2 of the longer questions in section B. So if you work that out, you've got 50 marks from question 1 and 50 marks from question 2. That means you should be spending 1 hour on question 1 and 1 hour on the 2 questions in section B. 50 marks in 1 hour, 1 mark per minute, if you get it right. So don't spend all your time doing section A and not answering section B, and the same in the opposite. The biggest problem that I've had is people do perfect answers for section A, take an hour and a half, and they have no time to answer section B. Again, that means that you don't get as good mark in the exams as you are capable of. So get your timing right. So if there's 10 marks going, my rough rule of thumb is 1 mark, 1 minute, as I said before. So once you've written for 10 minutes on a subject, if you can do that, there isn't any more marks to get. So don't tell me everything you know about a subject, filling up the exam book, because once you've got the 10 marks, you're not going to get any more. So put in the amount of effort that the number of marks in the question suggests. I'm also firmly of the opinion, as the song goes, that a picture is worth 1,000 words. So if you can draw a diagram and you can label a diagram to answer a question, I tend to give you marks for each of the labels. That makes it much easier than writing a whole paragraph, particularly if English is not your first language. And if you don't write in full sentences, I don't care. So you can put bullet points in if you want. I'm not testing you on your English, I'm testing on what you understood from the lectures that we've had. So don't worry if you can't think of the right word. As long as I can understand what you mean from the sentence, and I will read each sentence, that's okay. Don't worry if you get the punctuation wrong, that's not going to get anything. This is not an art subject. So, but if the meaning is not correct, you will not get the marks. So it's the meaning which is important. And please make it easy for me to mark. So if you answer question 1, write question 1, part A, very big at the start, so I know what I'm actually marking. If you want to get good marks, don't annoy the examiner. And that means make it very clear what they're actually marking. And it says on the exam book that you'll have to write in, you have to fill in which questions you've attempted. And it would be really good if you put question 1 part A, question 1 part C, question 1 part D, and then questions 2 and 5, something like that, down on that front book. So I know exactly what you've done. I would advise you to start each answer on a new page and leave some space at the end of the page if you've got material you want to add later on. If you write what you know and then come back to a question later, if you leave some space at the end, it's much easier for you to mark. But I don't mind if you run out of space, you saying, please see later in the book on page 10 or whatever, or after the answer to question 6 or whatever. You can put things like that, as long as it's clear that this is part of a previous question. So I will go through the exam book and I will mark everything that's in there. If there's something you do not wish me to mark, draw a big line through it so that I know that this page is not to be marked. Now, having said that, if you don't do very well in the question, I will look at that, and sometimes you'll get more marks from the bits you've scratched out. I've done that in the past. There is no penalty for doing more questions than you're asked for, except it will take you too much time and you'll be writing like this all the way through it. So if you're not sure which of 2 questions to do, particularly in section A, you could do 6 parts instead of 5 parts, and I will take the best 5. Right? So people in the past have answered every one, but if you do that, you tend to write less for each one, so the individual marks might go down. So as long as you do the minimum, what it says on the question, I will mark everything, and I will take the best answers for everything. I do not want to see you fail. I don't want to have to write a resit exam. So it's not in my interest for you to do badly. Right? So be careful what you choose. Choose the answers that you can get them the most marks for. But if you're not sure, don't worry about answering 2 questions instead of 1. For the short questions, that's okay. I would not recommend attempting more than 2 of the long questions. You haven't got time. This is a short exam, 2 hours. And the reason that it's short is I was getting exam books filled with information in previous years. You know, people wrote their entire life story about a particular subject. Because occasionally I set a question which is exactly what you did for your job. And so you know more about it than I do. And I can't give you any more marks than the 25 marks that there is for the question, however much you know. So, Section A, these are the sort of typical 10-mark questions. They can come from anywhere in the course. The first ones come from me. The second set of these questions come from Professor Gibson. There are only a certain number of these sorts of questions we can actually ask. So what I suggest you do is look at the exam paper, look at the sort of things that we ask, and make sure you're familiar with those from the lecture notes. I expect in your answers no more information than we've actually given you in the lectures. I don't expect you to go out and read lots of books and things like that. So there is enough material in the lecture notes to be able to answer all of these questions. So, describe the drop weight tear test and explain why it's usually used in a purchase specification. So, there's two parts to that question. Describe the test and explain why it's used. Describe the test. When you see a describe question, your first thought should be, can I draw a picture? It's easy to draw a picture of a drop weight tear test, and that's a good description of it. Why is it used? Well, then you have to think about the fracture properties of the pipe and the brittle fracture possibilities that are there based upon the material, so the drop weight tear test comes in. What particular aspect of the test might be important? The possibility of doing the test at different temperatures, ductile, brittle, transition behaviour. So these are all things there. So drawing that diagram might get you 4 marks. Doing the description of why it's used will give it another 4 marks. So you don't need to write anything more than about half a page in the exam book. What is the Bauschinger effect? Again, a diagram of the stress in one direction and the stress in the opposite direction with the strength dropping will probably be very good. Why does this affect the API strap test? Because the flattening process in the strap test will be pre-straining the material and you'll be testing it where some dislocation motion is in the opposite direction. Those sorts of questions you can answer quite easily, and again, it's probably about half the marks for each part of the question. So another point I would make is make sure you answer all bits of the question. Right, in order to maintain good corrosion resistance, what additional precautions are required when fabricating a duplex stainless steel pipeline compared to those with an ordinary carbon steel pipeline? You have to control the composition of the weld. You have to make sure that the austenite to ferrite 50-50 ratio is maintained. So there are precautions about the heat input, and there are precautions about the composition of the welding consumables. They generally have higher nickel content than what alloys that you're welding. But the whole point about it is you maintain the 50-50 austenite ferrite corrosion resistant composition. In this case, I think this is more a question that will be a text question with lots of description rather than a diagram. There isn't something obvious for that. What factors influence the size, structure and properties of the weld, heat affected zone in carbon steel, and how would that differ in stainless steel? Now that is a very hard question to answer in 10 marks, because there's lots and lots of things that you could say about that. But to boil it down, a carbon steel heat affected zone is that part where we go from a transition from a ferrite microstructure to an austenite microstructure and back. For stainless steel, it's always austenite, so there is not that phase transition. The other thing that happens in a heat affected zone is we get grain growth happening near the boundary with the fusion zone, and that happens for any material. So there will be grain growth in austenitic steels, and that may affect the mechanical properties, reduce the strength, reduce the toughness of the heat affected zone if it happens too much. So you might be talking about martensite formation for carbon steel, which doesn't happen with stainless steel. Now, we say the size, structure and properties. The size of the heat affected zone is the difficult one here, because I didn't specifically talk about the size of the structure. The heat affected zone in stainless steels is usually smaller than the heat affected zone in carbon steels, because the thermal conductivity of stainless steel is lower than in carbon steel. So the heat cannot escape from the weld quite so quickly. So that bit you may not know. So there are certain parts to these questions which you may not know the answer to directly. If you speculate and say, I believe that this is true, and if I think that that's a reasonable speculation, I will give you the marks for it. So I'm not expecting you to know absolutely everything about every material and things there. Yeah? Yeah?
Okay. So like for stainless steel, we have 4 types.
Yep.
So, and sometimes they have different properties.
Yep. Yep.
Which are different from the other.
Yep. Yep.
For instance, when you talk about the thermoconductivity of
Yep.
austenitic stainless steel,
Yep.
it's the opposite of duplex.
Absolutely, yeah.
So, can we generalize and say they all have low thermoconductivity?
In general, they all have lower thermal conductivity. Austenitic steels have very much lower thermal conductivity. Ferritic steels, because of the higher content of alloying elements, their thermal conductivity is pretty similar but slightly lower. And you probably could, if you look through the catalogues, find a stainless steel with a higher thermal conductivity if you tried very hard. But you can generalise. So that's why I say this question is very hard to answer, because there are lots of things that you could say, and you could make it more and more detailed. But there's only 10 marks. So I'm not expecting you to say everything you know about these systems. I'm expecting you to give me 10 good points in answer to the question. So unlike exams that some of you may have sat where there is an absolutely defined answer which is correct, and if you don't give that answer then you don't get the marks, I give you marks for being correct, whether it's what I wrote down in my specimen answer or not. So as long as you're correct and you answer the question, you'll get the marks. So I don't tie the marks down to specific points that I want you to make. I want you to demonstrate that you understand the subject. And the point you raised there would be a very good demonstration that you understand what's going on. So I'd actually give you marks for noting that not all stainless steels are the same. Sometimes when you get an advantages and disadvantages question, or compare and contrast, the best way to do it is to draw a little table. So you could put a line down the middle of the page, put advantages on one side, disadvantages on the other side, and then list factors, and you could say whether it was an advantage or a disadvantage. And particularly if you're comparing and contrasting, you can list the factor and you can say what it is for one material and for another material, or for one process and another process. So that also limits the amount you have to write. So compare and contrast, advantages and disadvantages. If you do it in a structure, in a table or something like that, that will reduce the amount you have to write and make it easier to show that you are comparing different things. So you could list the advantages in one column and the disadvantages in another column, for instance. And some things are both advantages and disadvantages. I mean, a manual ease of operation is an advantage if you've got to go down the hole to actually make a measurement, but it's a disadvantage if you want to get full analysis of the size of defect. So, you can have things which are sort of an advantage and sort of a disadvantage, and you might have to explain that. Working environment of an offshore lay barge compared to a pipeline spread. How does it affect the type of welding and inspection practices? So again, that's a comparison question. You might want to do that in a table form. Say that, you know, the welding processes, are they the same or are they different? The inspection processes, are they the same? Are they different? More automated welding, more automated ultrasonic inspection. Spread technique used on the land, double or triple jointed maximum on the lay barge. So you can start to see different things that you can compare directly. And the advantage of doing that is when you've got to compare and contrast things, you've got 10 marks going, you need 5 comparison points. Because you've got 1 before, 1 after. So 5's enough, yeah. So I don't expect you to write down, as I say, everything that you could possibly think about for this. That's why the exam is short. We don't want you to we want you to focus on answering just the question. Controlled rolling. Well, I've got in the lecture notes many, or in PowerPoint files, many pictures. There's a nice picture of hot rolling, cross rolling, controlled rolling, of the temperature cooling. And you can even add a comment about accelerated cooling if you want, but this doesn't ask for it in this question here. So again, a diagram is probably the best answer for this question. Now, this question has a word here, and a student a few years ago who had a question similar to this, explain what you understand by the term controlled rolling. The student wrote nothing, which was a correct answer. And he got 1 mark for it. But, but there was, yeah, if you say I understand nothing about it, you answered the question absolutely correctly, but you haven't given me 10 facts, so I can only give you 1 mark. So that's why I think you need to write enough about the subject to be able to get all the marks. What are the advantages of cold rolling? Well, the main advantage is grain size reduction to give you access to the higher grades without having to add alloying elements and sacrifice weldability. So you can see I've said, in answer to that question, very quickly to you a couple of sentences, and that will get you 3 or 4 marks just by those sort of couple of sentences, probably. But you need to amplify that just a tiny bit more to get all the marks that are available. That's why I say the answers to these tend to be about half a page of a book. So I suggest you put 1 exam book page for each of these answers, and then you can add anything to it that you want to afterwards. But no more than 1 page. Pipeline repair techniques that do not involve welding. I've underlined the word not. You'll be surprised how many students just write down every weld repair technique that they can think of. And yes, they may be in that group some techniques that don't involve welding. But if you start off with weld repairs and then list some other ones towards the end, I'm actually going to give you 0 for it because you haven't answered the question properly. So if it specifically asks for something which has a not in it or which excludes some things, do not write down the things that are excluded, because that will make me give you 0 for the question. It's one of the few times when I don't look and see what you've written and take out the good bits from it. If I specifically ask for things to be not included, don't include them. And that's Professor Gibson's question. He likes diagrams, but he also likes a bit more description of the diagram. Sometimes his questions are easier to do because they are clear, a diagram that you know exactly from the lectures. Sometimes they're not. That's just one of those questions. So you can see the balance there, though. The vast majority of the questions come from my part of the course, a few questions from Professor Gibson's part of the course. And that's really related to the amount of material in the lectures. It's just, you know, that's the limiting factor is how many different topics that are covered. Now, I know in this module I've given you an awful lot of material. So I don't expect you to know things in depth, but I do expect you to know the broad picture of everything. Because I think, certainly when you're making pipelines, if you're out in the field, you're not going to be focusing on one tiny piece of detail. You're going to be having to deal with any problem that comes along. And so a familiarity with a range of different conditions, a range of different processes, a range of different operations, that's what this is about. So don't feel you have to know the great details about everything, but the big picture, I think you do need to know. And that's what I'm looking for in the answers. So this is particularly true in the longer questions. Now you can see this is a typical long question. So there's 25 marks for this, 10, 5, and it goes over the page, 10. Right? So it's something like 2 or 3 of the short questions. And most of the questions that I set get a bit harder as you go through the questions. So there's a concept in the UK we call bookwork. Bookwork is just regurgitating, just repeating what you've already been told. It's almost a bit like a memory test, just to demonstrate you understand what you've been told in the lectures. So, describe the precautions required when undertaking hot tap welding here. There's a whole section in the lecture notes about doing that, and really I'm just asking you to parrot back to me what I've said to you there. And this question's got 10 marks, got 3 areas here. You need to describe the area and describe the precautions. So you're looking at 3 or 4 marks for each of these questions. So you only need to write 3 or 4 sentences. You don't need to write pages. Okay. So a long question answer is typically 2 or 3 pages in the exam book. Some people's writing is very large and it can be 5 or 6, but if you're writing 10 or 20, then you're doing too much. I had a student one year who would write on 4 lines across the exam book and write about 3 words per line. So it looked like he'd done an awful lot of writing. But I counted the number of words he wrote, and it was less than a student who just wrote on a single line. So he tried to make me think that he'd written a lot by writing very big. So we can see through those sorts of... again, diagrams. Diagram of what burn through means, probably very good. Hydrogen cracking, you can say where the hydrogen cracks occur. The better tearing diagram, again, probably the best way to do those things. Right. Before hot tap welding is carried out, it's usual to assess the pipe cooling rate by heating a small area of the pipe and measuring its time to cool. Why is this operation carried out? I may choose to ask in the paper a question like this, which is something you've never seen before. But the answer I'm looking for is very simple. Because when you're out in the field, you will be given a report, and often it's full of things you've never seen before, and you want to make some sensible decisions based upon it. So in this case, why is measurement of cooling rate important? Well, we've talked about cooling rates, and we've talked about microstructural effects and martensite formation and brittleness. So you know why cooling rate is important. We just haven't gone into this level of apparent detail. So you can answer this question quite easily, even though you've never seen it before, from that other knowledge. So pulling knowledge together from elsewhere in the course with what's in the question is what I'm trying to test. And again, it doesn't need to be too detailed. It needs to be able to show that understanding. So then it gets a bit more complicated. And as I said, these questions get harder as they go through the question. So, you know, you'd expect that. So there's a figure, which again you've never seen before, unless you've seen this exam paper, that shows the world cooling time from 850 to 500 and the pipe cooling time for world beads deposited onto pipes containing natural gas at various different flow rates. So the curves for various pipe wall thicknesses between 6.3 and 25 millimetres have been put onto the graph, and you've got two initial preheat temperatures. So this graph looks like this. So you've got the pipe cooling time, and you've got the world cooling time. And you can see there's a transition in this data. So it starts off, there's a linear relationship between the two, which is what you might expect, but then things curve over. Now the question gives you a clue, because it says here, the pipe wall thickness at which the transition from two-dimensional cooling to three-dimensional cooling occurs. And again, if you remember in the notes, when you've got gas flowing through the pipe, if the pipe wall is thin, the heat can go in and then can be carried away by the gas flowing through the pipe. That's two-dimensional cooling. If the pipe is very thick, then it's conduction into the pipe in all directions. That's three-dimensional cooling. So there's a transition from two-dimensional to three-dimensional cooling as we increase the thickness of the pipe. And also, this shows up in this figure. And what it shows up for, if you look at something which is very thick, like here, thick pipe, 25 millimetres, that curve is flat. If you look at the thin pipe, it goes up, starts to flatten off at the end. So, this one we know is definitely three-dimensional. This one we think is two-dimensional. So just by knowing that, you can then identify the curve in between those where it goes from this sort of behaviour to this sort of behaviour. And if you look at the dark curves, this one's got a bit of curve on the end, this one's got a little bit of curve at the start, but it's pretty much flat, this one's pretty much flat. So you might say that somewhere between 9.5 and 12.7 we go to this flat behaviour, which we think is the three-dimensional cooling case. Now you might say, well, what about this bit down here, where it's curved a bit? So you might say it's between 12.7 and 17.5 and 25. I will accept either of those answers, providing you justify why you've chosen that particular case. So you know the extremes, and you know there's a transition from one extreme to the other. How you define exactly where you get from one extreme to the other as part of that transition, that's up to you to write down. So this is a question where there is not a right answer. There is a right answer based upon what you write down as the condition for transition. And if that condition is reasonable, so horizontal behaviour or transition horizontal behaviour, whatever, you know, you can write those down. I will accept that. If you said, well, I've picked 9.5 because its curve looks different from all the other ones, then I'll not accept it. There has to be a good reason argued from what you know. So you will always have the information from the course to be able to answer these questions. You just have to think about what you've been taught means to be able to do it in the context of the question that's been said. And that's the harder question to say. It's worth 10 marks in the end. So you could actually get 15 marks if you knew everything on this question without even attempting that. And 15 marks will get you a pass. So if you're aiming for a distinction or something like that, you need to have a good go at these sorts of questions. But you don't necessarily have to answer the really hard stuff to just pass the module. There's a slight difference between temperatures, so you compare the solid curves to the dotted curves. That's okay. And what's the significance of these findings in terms of the ability to control the cooling rate of the welds of pipes of different thickness. How do you control the cooling rate? You look at that diagram. You've got different cooling rates here and here. What you'd like is something where you've got a very easy relationship. So if you've got a nice straight line, like here, you control the cooling rate basically by the thickness that you've got. Where you've got something like this here, the cooling rate is going to depend upon the local conditions that are around the outside. So in this case, it's much more difficult to control the cooling rates than in this case, because there's a very fixed relationship. So the implications are that it's easier to actually control the cooling rate in thick pipes or very thin pipes, but the ones in the middle, because you might have this transition behaviour, that's not necessarily so easy to control. What it means practically is people actually measure this. They have a temperature probe on the pipe, and they will heat a piece of pipe up to a certain temperature, and they will measure the temperatures by depositing weld metal on the surface of the weld metal and the pipe cooling, just to check in the environmental conditions that you're doing the weld that you get behaviour that you're expecting. And it has to be checked actually in the environment that you're doing the weld. So if you're welding onto a live pipe, you bring a pipe pup in and you do a weld next to the pipe, and you check that, and then you might even weld onto the surface of the live pipe a small amount of material, and you check that, and you make sure everything works with what you're expecting before you go and do the real weld that is going to be significant for your asset. So that is a harder question, and it gets harder as it goes through. And the long questions are basically like that. So another question that I often ask is a question about the selection of an appropriate grade for a particular job. So in this case here, you're constructing a new 1.2 metre diameter cross-country pipeline, 150 kilometres long, and you're given the gas conditions. It's dry gas at 85 bar. And I'm really talking about what you should make the pipe of, and the choice is between X65 and X80 in this case. So these are the sort of calculations that somebody might be doing when they're considering a new asset. Now, to start this off, you've got a nice question about advantages and perhaps disadvantages of the X80 compared to X65. So that leads you in. You know, things about thinner walls for the same internal pressure, easier to transport, all of those things that we talked about in the lectures. So there's plenty of things you can write down to get the marks there. Offshore, we never used those because we're worried about corrosion and other factors of reliability. The X80 is a much newer material. It's slightly more difficult to weld, so tends to be offshore is X65. But occasionally, recently, we've been seeing X100, X80 being used for trials. X80 is now approved in warm water applications. It's not so common in the North Sea because it's a bit cold. But then it's coming, you know. But the industry is more conservative. It chooses accepted and tried and tested solutions offshore because the cost of repair is very high compared to onshore. So anyway, you can write lots about that. There's plenty in the notes. So the next question then, you've got this. This is an application of Barlow's formula. And I've actually given you Barlow's formula in the question, so you don't even have to remember it. You need to plug the numbers in. Take a calculator to the exam. It's in bar. See, that's the thing. The oil and gas industry is notorious for working in mixed units. And yes, it will be 2T if it was SI units, it's 20T if the pressure's in bar. And that's in your notes.
Yeah. Do I really need to use that the formula with the 20, or can I use the one with the 2?
You can use the one with the 2 and convert. But the pressure's
I'm
in...
losing mark for using the one I know.
No, you won't use it, but then you'd have to convert from 85 bar into megapascals.
Okay.
So it's up to you, you know. As long as it's right.
Because it says there, like, assume this formula.
Yeah. Well, it's put there because I don't tend to want you to remember the formula. Some people, that one I actually probably would expect you to be able to remember. It's easy, but they're more complicated formulae around. I don't usually ask people to remember that. What I'm interested in you doing is making sure that you're consistent. So having a consistent set of units with the equation. You can work in millimetres and not in metres if you like, for instance, and it all cancels out. So as long as you're consistent, that's okay. And the key point, and I'll make this point now because I will take marks off for it, is significant figures in your answer. Right? The data is in 3 significant figures. Your answer is not more accurate than the data that is input into the equation, so your answer should not be more than 3 significant figures. So if you write down every figure from your calculator, although technically it's correct, you will, and I say will, get 0. Okay?
0.
Yeah. The biggest single mistake people make on calculations in this point is that they put in too many significant figures. And as an engineer, I think that is a hanging offence, right? Because your data, your answers cannot be more accurate than the input data. Because your calculator gives you an answer with 10 decimals, does not mean that any of those decimals are correct. 3 significant figures. If you're not sure, if it's 2 or 3, put in 3 significant figures, that's fine. I'm not going to worry about that. If you put in the 10 decimal places from your calculator, that is not fine, and you will get 0. Can I be any clearer? And that means that 7 easy marks become 0 easy marks. I'm just telling you that because that is the one thing that I'm very, very strong on. And I believe that no engineer should not know the accuracy of their data. I once saw a student saying they measured a pH, with a little corrosion probe, and the pH was 7.543, and that was the controlled pH for the experiment. So I asked him how he controlled that pH. If I put 1 drop of acid or 1 drop of alkali in, what effect does that have on the pH? Oh, it goes from 7.3 to 7.8 or down to 7.5. So your experiment was 7.3 plus or minus 0.5, because you could not possibly control it to the accuracy that you quoted. And if you write down that accuracy, somebody else is going to be expected to try and match that. And if they can't do it, that's going to waste a load of people's time trying to write a proper specification for everybody to use. So you write down the specification, what you did, exactly to what you need to do, and exactly as accurate as your equipment will allow you to do it. And that means knowledge of errors and significant figures is critical for an engineer, and I can't emphasize that enough. In this case, the rest of the question is actually quite straightforward, I think. Welding and inspection techniques suitable for an onshore pipeline. Well, we've got plenty of information from that in the lectures. That's straightforward for bookwork. Pipe to fitting welds. There may be a bit more complicated because it depends what the fitting is. We don't say what the fitting is in that case. So if it's a T-piece or something, some of the online ultrasonic measurements are not useful. So you could always say for simple fittings we would use this, and for more complicated fittings, welderlets, that sort of thing, we would have to use different magnetic particles, that sort of thing, yeah. And finally, overmatching. Again, there's a slide on overmatching early on in the course. You could describe that. Generally, you want the weld to be stronger than the parent metal so that the failure occurs somewhere in the parent metal, not in the weld. And that's why you do that. Because the parent metal is much more easy to control and inspect and check for defects than the weld actually is. Okay, next question. Weldability. Weldability tests. Again, that's in the notes. Carbon equivalent. Why is the maximum carbon equivalent specified? Again, it's in the notes. I haven't given you the equations there. If your memory is good, you can get marks by writing down the carbon equivalent equations if you want. If you can't remember it, explain what the carbon equivalent equation does, and you'll still get the marks.
Question for this one. Regarding the weldabilities, are you asking about the small scale tests?
Small scale tests, pup tests, full scale tests, they're all part of the weldability. Generally, you qualify the weld with small scale tests, but you actually check that that qualification works by doing the full scale tests, particularly the crane and lift tests. This is a question here. I won't bother going through it. You'll recognise that question. That's the assignment that you've just completed, or you completed just before Christmas. But 12 marks, so it's not everything in that assignment. So that question was put in for people that didn't have the memory of everything for the course. So when I give you something which I think is straightforward, you get lots of marks, but there's no guideline as to where the marks are coming from. So you need to be able to answer everything in that question. You can see there's various different, there's a sketch part of this, there's a describe part of this, and then there's a question to answer. So if you look at a question like that, you can probably divide it up into three, approximately equal marks for each part. 4 marks for the sketch, 4 marks for the description, 4 marks for answering the question. Now this question says, where would the weld most likely to be fail under impact loading? I would say that just answering where, you could say in the heat affected zone on the high carbon side. That answers the question correctly, but you wouldn't get 4 marks for that. If you said because the weldability is poorer because of the chance of martensite formation in the high carbon equivalent side, you'd get the marks. So just answering the what without a little bit of the why, you need just 1 or 2 extra things to get the number of points that are there.
What if I say in the coarse grain region of the heat affected zone?
So then you would get of the higher carbon equivalent side. So coarse grain would get you a mark. Of the heat affected zone would get you a mark, high carbon equivalent side would get you a mark, and possibly if you said due to martensite formation that would get you another mark. So a mark is a fact. So we need a few facts there to actually get the full marks. And the last question is a Professor Gibson question, so I won't say anything more about that. The same points apply. So in summary, what I think you need to be able to do is actually give me enough facts to give enough marks for it to pass. And the marks, you know where they come from the breakdowns in the question. So if there's 10 marks going, I need 10 facts, or a diagram with 10 labels, or something like that. Now you can't always do a diagram with 10 labels, so I need a description to go with that as well. If you give me enough facts, you will do very well in the exam. The biggest problem I find is people do not write enough. They'll give me a 1-word answer or a 1-sentence answer with 2 facts in it for a 5-mark question. So that you need to put a few more details down. As I say, I'm not interested in the English in the sentence, it's the factual content that I want you to put down there. Diagrams are easier to get marks with, and please answer every part of the question if you can, because another reason that people don't put enough facts down is they don't answer every bit of the question. I think that there will be one question or two questions in the short and one in the long from Professor Gibson, and the rest come from my part of the course. I think you can see they come from all of the parts of the course. But there's not a lot of marks going, so I don't want you to be able to give me the world's expert view on particular things. I want you to show that you understand it. And if you can cover that with sensible points, even if it's not what I wrote in my specimen solutions, which I did, and it's correct and it answers the questions, you will get the marks. Any questions? No? Okay. Right, well I would love everyone to pass, because as I say, I don't want to write a research paper. That's effort for me. So if you make it easy for me to mark the scripts, and you write enough facts down for me to give you the marks, I'll be very happy. And I hope everybody does well in the exam.
In Blackboard, I saw it one in 2014 feedback you have given that students were lacking experience in code expansion.
Yeah.
So what are you expecting?
Well, why do we do code expansion? Do we expand the pipe in order to make it round? That's one thing. To plastically deform it so that the well is done stresses, using the stresses. And we do it also to ensure that we have dimensional stability so that we can measure. So not only is it round, it's got the same size as all the others. So yeah, generally people would say they call the code expand for ovality removal, removing the top atom effect of the well, but not to relieve residual stresses and not to relieve. So there is stuff in the notes about that. It's just people didn't put enough reasons to just they just put one there.
Excuse me. It's relieve a little the residual stress as well.
Yes.
I was revising the lectures, but I couldn't find the advantages of the high frequency in use pipelines. Look at it.
Okay. Basically, when you have a high frequency, the current flows in the surface, so you just heat the surfaces, and the region is quite uniform. So then you have two pipes that you want to push together. When they're very hot, you can just push them together. It's a one-shot welding process, and that's its main advantage, that you can be in a position where you haven't got time to be able to do it. So if you're doing a diversion repair.
But I mean, for pipeline manufacturers.
Oh, for pipeline manufacture. Okay, again, this is a water pipe process. It's used for making very small pipes for that, very, very well. It can be used for making small pipes for gas and things very well as well. Now that we've got the quality, you can control it more than you can control the slider-based electrical resistance welding. So high frequency induction has got no contact on the surface, and that means that the changes in resistance as you slide along an oxidized pipe are less significant. So it produces a more reliable product now that we have the control of the electrical processes. Okay.
We have this AGI pipe installation above ground and buried. So apart from the normal fittings for buried,